So I'm Andrew Rowell. I'm a software developer at Expedia. I also occasionally do some computer science tutoring at MSU. And I'm enrolled in Georgia Tech's online master's program, so kind of got a lot going on. And today, I'm going to talk about making a machine learning API with AWS's serverless tools. So we're going to be looking at these today. We've got Serverless Application Model, API Gateway, Lambda, DynamoDB, and we'll also have a bit of machine learning in there. So why would you want to use these tools instead of setting up an EC2 instance or Dockerizing your app and putting it into ECS? These tools let you deploy a piece of code without having to worry about maintaining servers, making a Docker file, worrying about load balancing. There's a bunch of other details with infrastructure stuff that you have to keep track of, and this just kind of lets you throw some code out there, run it, hook it up to the web. Now, I started looking into these tools for a personal project. I just kind of wanted to see if they would be useful for prototyping something that I wanted to build. And SageMaker, one of Amazon's other machine learning tools, wasn't really going to be appropriate for that. So that's why I'm not looking at that in this presentation. I'm also more familiar with more traditional approaches where you'd set up an API and a service in a Dockerized service or on an EC2 instance. So Lambda and API Gateway, they feel like a shorter jump from that than SageMaker does. Going into this, what I wanted to make was an API that would let me upload training data and then query against it with test data. And the particular problem I look at here is what's called a classification problem, where you have data points and they have a category, and then you get a bunch of those data points with different characteristics about them, and then you try to estimate the category for a new data point based on its characteristics. So the AWS specific tools that we're going to look at will be SAM, the Serverless Application Model, Lambda, API Gateway, DynamoDB, and I'll look at those at a high level next. Serverless Application Model, I didn't actually know that this even existed before I started in on this project. It turns out that it lets me install dependencies for Lambdas a lot more easily than I would have had to deploy it with a CFT. When I looked into deploying it with a CFT, it seemed like I was going to have to set up an EC2 instance with Amazon Linux and replicate the Lambda environment and build my dependencies on there and then download those, put them in a zip, put that on S3. That seemed complicated. SAM just lets me specify it in a requirements.txt file like any other Python project. So that was really convenient. It's also, I think it's a cleaner deployment process. There's just two simple commands. You can store configuration for it in a file. And another neat thing about it is that it lets you run this stuff locally. So rather than having to upload to a new test Lambda each time, you can just run it all on your machine instead of having to test it in the cloud. Now, I didn't dig too much into that while working on my project, but I did find a good blog article about it on Amazon's blog, and I will share a link for that at the end of this. I also put it on my Twitter and LinkedIn. So Lambda is an AWS service that lets you run a piece of code without having to deal with any servers. It takes an event in, does something with that event, and then you return a response and do something with that in AWS. You can hook it up into all sorts of things. API gateway can send things into it. You can have queues pipe into it. And the billing on it is a little different from other services. So if you've used EC2 or ECS where you're paying for what you've got up and running, with Lambda, you're just paying for the time it's running. And so if it's not running at all, you're not paying anything. API Gateway is their serverless tool for defining APIs. You can configure throttling, authentication, the endpoints. You can use it to stub out responses. And it's kind of nice because you don't have to worry about scaling. And like Chris mentioned before, it's got a pretty generous free tier. DynamoDB is their serverless database solution. It's really simple. It's no SQL. It's very fast. And again, you're not having to worry about infrastructure. You're not having to keep database software up to date. It's really easy to make backups. And then the machine learning part of this is an algorithm called KNearest Neighbors. And it's just an algorithm that lets you load up the categorized data like I described before. In this project, I'll be loading up measurements of flowers and then their species. And then you can check new samples against that data to guess the category of the new samples. And the way it works is it finds the K nearest data points. So K is a variable that you can configure. So you can use 5 neighbors, you can use 3, and you can tweak that to kind of change how it behaves if you want it to be more general or if you want it to be more specific to your data set. And then on this next slide, I've got a graphical representation of that. So here we've got petal width on one side and petal length on the other. Can you see my cursor?
Yeah.
Okay.
Yeah.
So, suppose you had a sample with a width of 0.5 and then a length of 2, then it would see that these 3 neighbors are going to be the closest to that point, and it would categorize it as a setosa. And now I'm going to pull up the code and walk through that. So here's a GitHub project. If you've played with machine learning before, you might have seen this data set. It's measurements of the petals and sepals of irises, and then it uses that data to correlate to the species. And so it's a popular data set for testing out different machine learning algorithms. And a lot of times you'll see this being used with KNearest Neighbors. Here's the template YAML file, and this is what SAM uses to define the infrastructure that it deploys. So we define our API here, the top level object for that. Our DynamoDB table is set up here. We call it iris data, and we just have the ID key being put in there for each row. We have the role, the IAM role that lets the Lambda put things into DynamoDB and get them out, read them out. And then here, I define the 2 lambdas that we have. One is a lambda with code that puts flowers into the database. So this is kind of our training or data adding Lambda. And then this test Lambda is the one that actually runs the KNearest Neighbors on the data set. So it pulls that data out of DynamoDB and puts it into KNearest Neighbors and then gets the prediction out of it. This is a permission to let the Lambda run for both of those Lambdas. More template for the API. So this defines our endpoint for putting that data in the API gateway so we can make a post call to it. And then here it's saying which parameters are passed in the request. So this is hard coding those parameters that get sent into the Lambda. And then the response is just an empty 201 status code. And then here is the API endpoint for getting the classification of new data samples. And there we put in some of the same parameters and get a response out that's just going to have the species. So it just returns a string with a number in it. And then this is some more configuration of the API for those parameters for getting the flower and adding the flower. And then this is adding that part of the path, the kind of flower endpoint that we can get and post to. Now I'm going to pull up the code for the Lambdas themselves. So we've got this requirements.txt, which is used by SAM to add this scikit-learn library to my Lambda. We've got this add flower Python file, which is the Lambda that stores the data in the database. And all this is doing is opening up that database and then putting in an item with the same parameters that I passed in. And with DynamoDB, you can specify new columns whenever you put in an item. So I'm not having to worry about the schema on that. And then it just returns a success message. And then here's the code that does the heavy lifting. This is the code that builds that KNN model. So what it does is it reads the flowers, all of the flowers from DynamoDB, puts it into a training set. So the X train is the characteristic data for each flower, so all the dimensions of the parts of it. And then the Y training data is the categories, the species. And when you use the KNearest Neighbors classifier, you pass those in, and so it just stores those data points in the classifier. And then here I'm passing in the characteristics of the data point that I want to predict the species of, and then passing it into KNearest Neighbors, and it's using that KNearest Neighbors algorithm to predict the species of the flower here. And then it puts that in the body of the response, sets the status code to 200, and sends that back to API gateway. And I've got a couple of helper Python scripts here. So I've got upload data. And what this is doing is it takes that iris data set and splits it into 80% training data and 20% test data. And the reason I do that is so that I give the classifier part of the data set, but it doesn't know the correct species for all of the data. And so I use that 20% test data to see if it's actually working, if it's accurately able to predict the species. So this is just CSV parsing code, I'm turning the species into numbers for the classifier, randomizing it. And then this iterates through and makes a post call for each of those data, for the training data points to upload them. So this is hitting my API endpoint to upload the training data. And then it creates a file called test data CSV, which is the rows that it didn't use for training data. And it writes all that info to that file. And then that's all that script does. And then test data goes through that test data CSV that the previous script built and does some more CSV parsing. And then for each one of those, it makes a call to the get call to predict the species for that data point. So it's using the API to make the prediction there. And then this just prints out if it was an accurate prediction or not, if it matched what we had in the data set. And then next, I've got a recorded demo on Ask Cinema of this actually in action. So this is the commands, the two commands, these are the two commands to build and deploy it with SAM. So the build puts together that Python code, and the deploy uploads it and then deploys the stack based on the template. Oh, another thing I forgot to mention about the serverless application model is that the templates for that are a superset of CloudFormation templates. And in my template that I used for the infrastructure to set up the database, the API gateway endpoints, I did use some CloudFormation template in there because I started out with this project thinking that I was going to be able to use CFTs. And then when I ran into needing to add dependencies for the Lambdas, that's when I found out about SAM. So you can use some CFT stuff in a SAM template and mix them together. So there it's deployed. And then here I'm uploading the training data. So that finished uploading. Now I'm going to run the test data script to see how many of the samples it can accurately predict. And here we see that it's getting a lot of them right. Not quite all of them, but most. And then here are some example curl calls to the API itself, just showing how I can pass in those parameters of the data point and then get a prediction back. Okay, so now there are some reasons why you might not want to do this. These tools can get expensive on the high volume end. I couldn't find any case studies online, but I have heard of Lambdas being rewritten as Dockerized services due to cost. That said, at a low enough traffic level, Lambda should be cheaper because you're only paying for when you run it as opposed to paying for an ECS instance being up all the time. If you're making an API with different endpoints, many different endpoints, this can be a hassle to maintain, or if somebody wants you to have like a prod set of Lambdas and a test set of Lambdas, then that can get out of hand. And also, if you're really familiar with other tools, like if you were very familiar with ECS and Docker, or really familiar with managing servers, it might just be faster for you to put something together with a framework like Flask or Express with JavaScript and run it on a service that way, rather than having to learn how to use these serverless tools. But at a low enough traffic level, these can be cheaper, again, because you're only paying for when you run it, as opposed to paying for something that's up all the time. I think that it has less prerequisite knowledge than setting up ECS or EC2. If you're not familiar with Docker or managing servers, and you're in a role where you've mostly been doing things with data on a local machine with Python scripts, and then somebody asks you to make an API out of it, it might be easier to transition to this than to learn how to use the server tools. And there's no servers to manage. That's its own skill set. So you don't have to know how to do that to use these. Other caveats. I made this simple project to find out if these tools would be worth using to prototype another project. So I kind of threw this together really fast. Wouldn't throw something like this out into production the way it is. It builds the model on each test query, and that's not a problem for the algorithm I use for KNearest Neighbors, because KNearest Neighbors does most of its heavy lifting on the prediction side. But if you were using something like neural networks or linear regression, where more of the work was in building the model than using it to predict, then you wouldn't want to do that. You wouldn't want to be doing all that processing each time you made a prediction. The code is also only set up for this iris data. I didn't take the time to make it generalized to different dimensions of data, being able to put different parameters in. So you'd have to go through and change all those manually. And also there's no authentication. So I just put the API up to do that demo and then take it back down. I'm not leaving it up all the time. If you had something that you were going to leave up all the time, you would definitely want authentication on it. So that's all I got for serverless ML. If anybody has any questions, I can answer them now.
How long did it take you to build this whole thing?
Once I learned how to use the tools, it is something you could easily do in an afternoon, just not even a few hours. Probably the most difficult part was learning how to use the serverless application model. I didn't even know it existed before I started the project, so it was very new to me.
Okay.
Andrew, I wanted to ask you what kind of constraints are there using lambdas in terms of the complexity of the programs you're running? You loaded the scikit environment into a lambda, is that right, or is that something that's already provided by AWS?
So I loaded it into the Lambda. I'm not sure what restrictions there are into what libraries you can add through that requirements.txt. I think it should just be anything you can install with the Python package manager. There's also a limit on the runtime for lambdas. I looked it up real quick. Looks like you can run lambdas for up to 15 minutes per execution. So you also wouldn't be able to use this for something that would take a very long time to build a model. But you could do something like build your model on a machine and then store it somehow in a way that you could easily retrieve it with scikit-learn. I believe that scikit-learn has ways of storing and retrieving models, and so you could use that to make predictions quickly.
I had another question just for clarification. When you said that you're running it locally, what did you mean by that?
So I didn't get a chance to play around with running this locally. I was really just trying to rapidly prototype something, so I didn't dig too much into that part of the serverless application model framework. But from what the documentation says, you can set up a local instance of DynamoDB. You can run these lambdas locally on your machine in Docker containers, so you don't actually have to deploy it out to Amazon servers to run those things. It looks like you should just be able to do that without even having an internet connection once you have all the right resources downloaded.
Great.
There's also debugging tools for that framework for running these things locally. So it sounds like you would have a much shorter cycle time for testing changes you make and debugging problems. If I were going to use this on a daily basis, I would definitely look into setting that up.
Are there any costs associated with using it locally?
No.
So does that mean it didn't cost anything to build this, or was there like a few cents cost from using the different tools?
Well, I think I stayed in the free tier for what I did on Amazon's servers with this stuff. I think Gareth was asking if there would be a cost associated with running these things locally with the SAM framework. I believe I stayed in the free tier with what I was doing, not locally.
Okay.
Well, thank you very much for sharing tonight, Andrew. Great content.